Good morning. Today we will discuss about the sample and first derivative method, which is widely used for determining the peak value of a signal. Now, coming to the last lecture, we have discussed about the components of digital processing relay subsystem. We have seen the significance of memory, the CPU, and the other components which are generally present in the digital processing subsystem. And we have also seen some random specifications of a digital relay. Also, we have seen the complete block diagram, the representation of a digital relay as a single unit. These things we have covered in the last lecture. So, in the present lecture, we will discuss about the sample and first derivative method, which is generally used for determining the peak value of signals. So this is the start of unit number 2, which deals with different techniques which are generally employed for determining the peak value of signals. I hope that by the end of this lecture, you will be able to describe this particular method, which was widely used in olden days. Now we are employing Fourier transforms and also Walsh techniques. But let's have a quick look at the sample and first derivative method. So I'll start with the introduction. Why do we need peak values of signals? Then we will go with the sample and first derivative method. We will determine the peak value of signal, and also we will determine the impedance, both its magnitude and also the phase angle, with the help of sample and first derivative method. Coming to the introduction, you know that peak values of any signals are very significant in power systems, because in order to understand the status of the power system, we generally look at what is the current value and also the peak value of the system. So at fault durations, particularly during the faults, if we know the peak values, then it will be easier for us to determine what is the maximum amount of current and voltage that can be expected during a fault. So based upon this maximum values of current and voltage, we will be designing the protective devices, the circuit breakers or the fuses or the relays, everything. The design is based upon the maximum values of current. Let us suppose if I do have a transmission line like this, it is normally supposed to carry 10 amperes. Now, let us suppose if there is a fault which is happening on the power system, then maximum allowable current is 15 amperes. So, at any point of time, I must know what is the peak value of a signal. So, based upon these things, I will design suitable protective equipment, such as my circuit breakers, etc. Apart from this, the maximum allowable current which is passing through this one, or the maximum current which is passing through this one, based upon this, I will come to know about the thermal stability of my power system. And also, sometimes these temperature changes also, they will affect the resistances, and it will again affect the currents. So dynamic stability also will be understood with the help of your maximum values of currents and voltages. So it's always good to know about the peak values of the signals which are running in the power system. So our job is to determine the peak values of whatever the signals may be. In the last unit itself, we have taken an assumption that we have seen that in the transmission line, first of all, we'll use some sort of transducers, and next we will use some sort of surge protection circuits, and next we use filters, LP filters, and after that we will use MUX, and again we will use analog to digital conversion, and then we process these things. So we will be on an assumption that whatever the signal which has come to this processing is purely or mostly a sinusoidal signal, which has been exempted from harmonics. So based upon these assumptions, we will start how to employ these algorithms. We will now try to understand different algorithms, and then we will try to apply them for determining the peak values. In the olden days, we used to employ the sinusoidal based algorithms for determining the peak value or a squared peak value of the waveform. So they were in two types. One was a sample and first derivative method, and then improvement of that one is a first and second derivative method. So sample and first derivative method, an improvement of that one is a first and second derivative, and the other one is instead of derivative, they use it to have 2 or 3 sample methods, 2 sample method and 3 sample method. So try avoiding the derivatives because it was a little bit complex one. So in this lecture, we will see how sample and first derivative method works out. So I'll assume that. So first of all, let's try to determine the peak value. I'll assume that the incoming signal is a voltage. Incoming signal is sinusoidal in nature. So I'll take this incoming signal as a voltage signal. So I'll take a sample voltage signal. So I'll take it as V of t is equal to some Vm sine omega t. Let us suppose I'll take the phase value also. Let us suppose this is this omega t plus theta. Okay, so this is my signal, and I'll represent it as V is equal to Vm sine omega t plus theta. Now, if I take first derivative of this particular one, so dv by dt, which I'll represent it as V dash, this is equal to Vm sine omega t will become cos omega t plus theta. The internal derivative is omega, right? So if I bring this omega to here, what I'll get, V dash by omega is equal to Vm cos omega t plus theta, right? So this is my V, whereas this is my second equation. So I'll take this as first equation and I'll take this second equation. So you square these equations and add them. So what I'll get here, V square plus V dash by omega whole square is equal to, what is the square of this one? This is Vm square sine square omega t plus theta plus Vm square, this is the one, cos square omega t plus theta. So if I take Vm square as common, I'll get sine square omega t plus theta and cos square omega t plus theta plus cos square omega t plus theta. You know that sine square plus cos square is always equal to 1. So this is equal to Vm square. Right. So this is the expression. So if I write it again, V square plus V dash omega whole square is equal to Vm square, where V is the instantaneous value of that particular signal and V dash is the instantaneous value of that signal, sorry, first derivative of the value of that particular signal. So now what is Vm now? I'll take it as V square plus V dash by omega whole square. See, now you have obtained the maximum value. If you know the original signal, and if you know the derivative, first derivative of that particular signal, and if you know the frequency of that signal, then you can determine the maximum value of that signal, right? So in this way, we can determine the peak value of any signal using the sample and its first derivative, whether it is a voltage signal or a current signal. If it is a current signal, then I will take it as right. It depends upon the frequency also. Now, determining the magnitude of impedance, right? Sometimes we are supposed to process two signals. One is voltage signal, the other one is a current signal, and we need to determine the impedance. So how to determine the impedance? Because particularly in distance relays they do work upon impedance, right? So if Z is less than Z naught, then automatically it may go on for tripping. So we need to determine the impedance all the time. So how impedance is being determined using this sample and first derivative method. In impedance, we do have two things. One is the magnitude of impedance, the other one is the angle of impedance, right? So first of all, let us try to determine the magnitude of impedance. So I'll take two signals. One is V, the other one is I. I'll take these two as my signals. And I feel that there is a difference of theta phase angle between these two. Okay, I'll take it as Vm and this is Im. Okay, these represent the maximum values. Now, when V is equal to Vm sine omega t, you know how to determine Vm maximum value, right? It was square root of V square plus V dash by omega whole square. If I is equal to Im sine omega t plus theta or phi, whatever you feel it as, then Im is equal to, again, I square plus I dash by omega whole square. Now the magnitude of impedance is always equal to Vm by Im, right? So it is very simple that I will directly utilize these equations. Right. So this is my magnitude of impedance. It is the square root of V square plus V dash by omega whole square by I square plus a simple one for determining the magnitude of impedance using sample and first derivative method. Now let's try to determine the phase angle of the impedance. Now I'll take the phase angle of the voltage as theta V and the phase angle of the current signal is theta I. So the phase angle of the impedance is generally given by theta V minus theta I. Right? We already have seen V is equal to Vm sine omega t. So omega t will become theta V. So I'll write it as Vm sine theta V. And for the current, we have already seen that Im sine omega t plus phi. This I am writing it as Im sine theta I. Right. So if I apply derivation for this one, V dash is equal to what I'll be getting. This is Vm. Sine will become cos. The internal derivative of theta V, which is equal to theta V is equal to omega t, right? If I internal derivative, I'll get omega, right? So this is omega Vm cos theta V. Whereas similarly, I dash will become Im omega cos theta I, right? So if you carefully see V and V dash, if I take V by V dash, what I'm going to get, this is Vm sine theta V. This is omega Vm cos theta V. So Vm will go away. So this has become tan theta V by omega, right? If I take the theta V, this is omega will go here. So what I'll get tan inverse of omega V by V dash. Similarly, what is theta I? Theta I I'll get tan inverse of omega I by I dash. So from this, what I'll get, angle Z is equal to, very simple. This is tan inverse omega V by V dash minus tan inverse omega I by I dash. So V and I are the samples, whereas V dash and I dash are the first derivatives. So if I know the samples and also the first derivatives of the signal, then automatically I can determine the peak values of the signals. I can determine the magnitude of impedance, and also I can determine the phase angle of the impedance also. So this is one of the easiest methods for determining the impedances and also peak values of the signals, but it has its own limitations, right? it is very sensitive to noise and other inaccuracies. See, if you do have a multiple harmonic, let us suppose if it is Vm sine omega t plus some V naught into sine 2 omega t, we can't derive it directly and we can't square it very easily. So that is a big problem for this one. And also, if the signal is not sinusoidal or having multiple peaks, as already said, if it has harmonics, then this method may not work well. And also, if for a large data set, this is a little bit computationally expensive one, because finding derivative of a signal is a little bit tougher task. And the accuracy of the derivative calculation, this particularly, determining the derivation is a little bit complex task, right? So the accuracy of the derivative calculation, it depends upon the sampling rate and the amount of noise in the signal. If the sample rate is too low, then the calculated derivative may not be too accurate. If the sample rate is too noisy, and the signal is noisy, then the derivative may be difficult to calculate. So in either case, it may not be suitable. So the conclusion, the sample and first derivative method is the simplest method, which is used for determining the frequency and also amplitude of a sinusoidal wave. And the method basically involves taking the sample at discrete time intervals and then using the first derivative, the sample, to calculate the frequency and amplitude of the wave. And it is also used for determining the magnitude and phase angle of the impedance, suitable for both continuous and discrete time signals. So I hope that you are able to describe this method, and in particular the limitations of this method when you use it for determining the peak signals. So this is your essay question which I'll be asking in particular with any application. So for more information, go through this text a bit. We'll discuss a little bit more in the class. Thank you.